All right, back to our discussion of bone. We've talked about the bone cells. We've talked about the cells that build bone, and we talked about the cells that remodel bone. But we haven't talked about the matrix so much. So now we're going to talk about the osteoblasts and the osteocytes and how they deposit two categories of components of bone matrix. And again, I'm going to compare this to pouring concrete. Before you pour concrete, you lay down the rebar, those metal rods. Well, for our bone matrix, that rebar, that's going to be our organic portion, and principally, it's going to be the collagen fibers. And so that's going to provide quite a bit of strength. And we don't think of bones being flexible necessarily, but collagen, much like we see the collagen in cartilage, it provides some degree of flexibility. But we're going to reduce drastically the flexibility of collagen by now pouring in the concrete. And just like concrete, this material that's going to flow between the collagen fibers is inorganic. Now, what distinguishes an organic molecule from an inorganic molecule? Carbon. So our molecules like collagen are proteins, they're organic molecules. But the hard matrix portion is going to be what is termed hydroxyapatite. That's a calcium phosphate material. Now, the way bone cells do this, they can't form calcium phosphate hydroxyapatite inside the cell because this is a hard substance. It's like a kidney stone. And so what the cells do is they begin to concentrate calcium and phosphorus inside this vesicle. And then they basically push the vesicle out of their cell membrane, and now this vesicle is just floating out in space. It's a cellular fragment. And inside the membrane of these vesicles are pumps that continue to pump in calcium, continue to increase the phosphate. And as you increase the concentration of a substance, a solution, you supersaturate that solution. And invariably, when you supersaturate a solution, what's going to begin to form? Whether it's salt or sugar, you probably did this in elementary school or middle school. You get this supersaturated solution and you put the string in it. What starts to grow? Crystals. And so as you increase the concentration of the calcium phosphate in these vesicles outside the cell, you start to form crystals of calcium and phosphate that grow larger and larger and rupture through the vesicular membrane. And now you've got this growing large crystal situated between the collagen until all these crystals grow and coalesce together into our solid inorganic bone matrix. So, collagen provides strength. The organic portion provides the hardness to bone, both of which function to make our bones strong. But if we didn't have one or the other, we would have a problem. If we didn't have collagen, our bones are going to be extremely brittle. Now understand, when we think about brittle bones, often we think about bones in the elderly, the geriatric population. Their bones are in fact brittle, but it's for a different reason. It's not because of a loss of collagen. But I think you can also imagine if we've got collagen, but for whatever reason we don't have sufficient amount of hydroxyapatite or calcium phosphate, our bones are going to become flexible. They're not going to be as hard, so they're going to bend. And here we have two children. Clearly, I think it's easy to see that they're malnourished. And it breaks my heart to think that in our culture, in our society, where we're debating, do we get a Galaxy 8 or an iPhone X, we've got people like this. People that really use help. And we usually don't think out of sight, out of mind, right? Do you know that there are people that live in third world countries, thousands of children every year? You know what they die from? They die from diarrhea. because their water is infected with parasites. If they just had clean water, I'm sorry, it's kind of my soapbox, so I'm going to get off of that. But in addition to being malnourished, maybe they have sufficient calcium. But what do you think these children are missing from their diet? Or what are they not getting daily a sufficient amount of? Vitamin D. Because you've got to have vitamin D to absorb the calcium through your intestinal lining. So whether you don't have enough calcium or you don't have enough vitamin D to absorb the calcium from your diet, your bones are going to be weak and flexible. And that bowing of the bones is characteristic of what happens because of that, especially, again, in malnourished populations. So the bowing of the bones. I mean, your bones are strong. You're born with straight bones. But because of environmental effects, your diet, lack of sunlight, vitamin D, or because of the stresses that are put on your body, your bone is going to be shaped and reshaped continually. And so what cells form bone? Well, we've got our full-grown adult bone cells. They're all going to start with osteo because osteo means what? Bone. So what are our adult bone cells? Osteocytes. But we're going to have, during early embryonic development, when your bones are really just starting to grow, we're going to have those baby bone cells, and they're osteo who? Blasts. So these are our osteoblasts, this little illustration. And do you see how it looks like they're crawling across this woven, fibrous network? This artist is trying to illustrate the collagen fibers, and what the cells are leaving behind is our inorganic bone matrix. Does it kind of give you an idea of what's happening, the two different categories? So the osteoblasts, they produce both our organic and inorganic portions of the bone. But under stresses, under environmental pressures, sometimes our bone has to be remodeled and reshaped. And so we also have cells that remove bone, and these are our osteoclasts. They remove both the organic and inorganic part. They remove the organic part by producing acid. Now, again, we've got our hydrochloric acid producing cells in our stomach, but these cells will form a tight seal around the outside of the bone. And they will secrete materials, including hydrogen ions, into the space underneath the cell. And they form like this suction cup seal around the edges. So just the area underneath the cell is going to have a low pH. And it's going to be acidic. It produces carbonic acid. Well, that's going to dissolve the calcium and the phosphate, the inorganic portion, which reveals the organic collagen molecules, which then the cell uses enzymes to degrade. It removes everything. But I think you can envision, too, this remodeling process to maintain homeostasis. And what's sort of a word to help somebody understand homeostasis? What is it? Balance. It's a balance. So for bone to maintain homeostasis, when you remove bone matrix, what do you have to have an equal amount of? Bone formation. As you remove it, you have to replace it. If you remove it too quickly and you're not replacing it fast enough, that's what happens with your bones as you become older. That's how your bones become thinner and more brittle. And we'll talk about that when we get to the aging part at the end of this unit. But here we have a histological slide, and I think y'all have seen some of this in lab already. The only cell you're going to see embedded inside the bone is our adult bone cell. And what is that? Osteocyte. The baby bone cells are going to be on the outside building up bone. And those are the osteoblasts. And when you see this really huge multinucleated cell, especially sitting in a depression where it has dissolved and enzymatically removed bone, you know that is an osteoclast. And just as a freebie, because I like the word for some reason, the little depression that the osteoclast sits in, did you get that name? It's called Hauschup's lacuna. I don't know why, just kind of fun to say. I guess Dr. Hauschup. How would you like to have that name? Hauschup. Anyway, that's his lacuna, and that's where the osteoclasts sit. So that's our cells that make bone. That's our matrix that make bone. And we're not going to name the bones. Y'all have done that in the lab. We're not going to name all the bumps and the grooves and everything else. Y'all have already done that. But when we look at the categories of bones, are we good with the long bones? What are some of our long bones? Femur, humerus, tibia, fibula, radius ulna. We can pretty easily distinguish the longs from the shorts, right? Carpals. What's the companion of carpals? Tarsals. How do you keep them apart? Tarsals, toes. I always did tarsals, toes. But I heard someone a couple of years ago say, well, they like to remember carpals because you drive a car with your hands. Whichever way it works. But we got the short bones, the same length and width, relatively speaking. We're good with the flat bones, right? The bones of your skull, principally the top part, the brain case, the calvaria, these are your flat bones. Your ribs are fairly flat. And we're going to see all these bones are sort of made of the same stuff. But the flat bones are going to be formed in embryonic development very differently than our long bones. And we'll talk about those next week. Irregular bones. I like irregular bones because that's like the miscellaneous category, right? Connective tissue. What was connective tissue? That was our miscellaneous category for tissues. Well, irregular bones, that's our miscellaneous, because how would you describe a vertebrae? What kind of shape does a vertebrae have? Round with spiky things? I mean, come on. You know, it's irregular. And then the last one that I like to throw in here is the sesamoid bone. And this is essentially your kneecap, because your kneecap is not directly attached to or connected with any other bone. And the kneecap, the patella forms inside the patellar tendon. The tendon comes from your quadricep muscle, stretches over your knee and attaches to your lower leg bones. And so your kneecap just sits inside that tendon, and you can kind of move it around, and it's really kind of weird. But that's what enables some surgeons. Has anyone had an ACL replacement within the last 10, 20 years? Oh, y'all were children 20 years ago. What am I talking about? Be about that long. But they did a patellar tendon graft. What kind of graft did you get?
I just had a repair.
Oh, just a repair? Oh, man, they can do that now. That is so cool. They use your own blood. And I wish they did. Well, yeah, we didn't have computers back then. Anyway, they used the patellar tendon graft because they took a chunk of the patella, a portion of the patellar tendon that's attached since it's within the tendon, and then I believe it was a bone fragment from the tibia that tendon connected to. So it looked like a Q-tip, if you can think of it like that. Bone on each end with tendon in the middle, and then they screwed that into the joint of my knee to make me a new ACL. So that was like 23 years ago, and I think it was sort of a newer procedure at the time, but I've had zero trouble with it. Knock on wood, where's some wood, please. But I've had zero trouble with it. But that's what enabled that to be used, is because of that sesamoid bone and the tendons that then are attached to it. So flat bones of our cranium, long bones, irregular bones, and the short bones. Those are just the categories that we have of bones in the body. Now that's the shape, categorized by shape. But within those bones, we're also going to have osseous or bony tissue of two different types. The first type we're going to talk about is compact bone. It's called dense bone, or it's also called cortical bone. Now, these terms, cortex and medulla, you should go ahead and learn those and commit those to memory. You're going to see these in a lot of anatomical descriptions. Cortex means outside, the outer portion of. Medulla refers to the middle portion. So you can think medulla M for middle. Cortex is the other, because I can't figure outside with C, cortex. So watermelon, for instance, the meat, the red part of a watermelon is the medulla. The rind, the clear white part on the outside, that's the cortex. And so when they say cortical bone, I think you can already envision that if you look at a cross-section of bone, the outer portion of that bone is going to be cortical or compact bone, whereas the inside part, the spongy bone, it's often referred to as medullary bone because it's more toward the inside of that bone. Now, our osteons, which we're going to see in the next couple of slides, and we'll go through it fairly quickly because you've already got that in lab, but our osteons are going to make up about 80% of the bone mass, this solid, strong part of the bone. But the spongy bone that's more on the inside are made up of these little pieces of bone that are all interconnected together, and these little pieces are called trabeculae. And this makes up about 20% of the bone mass. Now, what disadvantage can you see immediately by having bone made out of this versus that? Not as strong. Trabecular bone is not as strong. But what's the advantage of having trabecular bone versus compact bone? It's lighter weight. And in fact, when you look at birds, their bones are even hollow and more of this spongy bone to save weight. If their bones were more of the compact type, they would be too heavy to get off the ground. And in fact, when you look at trabecular bone, there's still quite a bit of strength there. Because if you've ever gone to New York or you've gone to San Francisco and you go across these really big bridges, those things aren't solid that are holding you up. You ever gotten on a bridge and just got real nervous? Like, ooh, how strong is this thing? So the trabecular formation is going to be strong, but it saves weight than what we see with our compact bone. So, compact bone, these are our osteons. And even though almost every lab manual, every textbook is going to show our osteons like a wedding cake, understand that these are just barrels that have these concentric rings that are laid down, these concentric lamellae. And these lamellae are centered around the central canal. Now, another word for that space on the inside is also called a Haversian canal, because I guess Haversian is the one that described this structure and pattern. But when you look at the concentric rings of our osteon, which of our rings is the oldest? The outside ring or the inside ring? Which is the oldest? I heard the outside ring is the oldest. Now, we think of a tree, when a tree grows, it just grows out and out and out and out, and the youngest is on the outside. Well, osteons grow in the opposite direction. The central canal is large at first, and it lays down that first ring because all the cells have to be connected through the canaliculi. And so the next layer that's formed gets put on the inside, and the inside, and the inside, and the inside. So the smaller the central canal, the older that entire osteon will be. Now, just another look. This is a scanning electron micrograph of an osteon. There's our central canal with stuff in the middle, meaning blood vessels and nerves. Has anyone broken a bone in here? Does it hurt? So you are painfully aware. See what I did there? You're painfully aware that there are nerves that are present in the bones. And many times when you break a bone, you bruise. You have bruises in those locations because of all the blood vessels that you broke while the bone was broken. So bone is living tissue. Again, just to kind of repeat that, unlike the enamel of our teeth. And so within our osteons, we have the transport of materials from the vessels of the central canal outward to all of our osteocytes. And someone said last time that they wish they had seen this picture in lab because it makes the canaliculi so much easier to see. And the other picture we saw, the black and white picture. But have you ever looked at this osteon picture, and do you see how all the canaliculi are always pointing toward the central canal? No matter where you see the canaliculi here, they're pointing this direction. These canaliculi are all pointing in that direction. That just shows you the transport highway from cell to cell to cell of material going outward to the cells and waste products being transferred back to the venous system to be removed. So the osteocytes, using their canaliculi, transport materials to and from the blood vessels. Because all living cells have to be fairly close to at least one capillary system. And that system is going to be present in our central canal. Now, spongy bone, or medullary type bone, it's going to be more toward the inside. And in this picture here in the upper right, you can see the white compact bone that's lining the outside versus all of the trabeculae of bones that's present in the top portion of the bone here and down further into the deeper portion. That provides the strength but yet lightweight. It's also going to provide a lot of spaces within which our progenitor cells for our red blood cells, our white blood cells, our immune system, those are all going to be present within these spaces that are part of the bone marrow. So again, we got a lot of strength. We're resisting stresses, but it's not going to be nearly as heavy as if we try to fill this entire thing with compact bone. What's the other advantage of having spongy bone? And you can see what percent of our bone is spongy versus compact. What's another advantage of having spongy bone? It's lighter weight. What about from a cellular aspect? Which has more osteocytes, compact or spongy? Compact's got a lot more osteocytes. You have a lot more osteocytes, you're going to have to provide a lot more resources, including glucose to produce ATP. So trabecular bone saves energy. Trabecular bone doesn't have to have the same requirements for nutrients and energy that compact bone has, because there are fewer living cells just because there's less bone mass in the trabecular bone. All right, our bones. First class said y'all went through this in lab, so we're not going to spend a lot of time on this again. When we look at our long bone, what do we call the shaft? The diathesis. This is going to be the lever part of the bone. Because if you have ever had to change a flat tire, you have to get those lugs off, and you go to your trunk, and that little tool that comes with new cars now, that little bitty tool that you can't get a grip on. No, if you can get the old-fashioned tire tool, the one that looks like a plus, you have a lot more what? Leverage, because it's longer. And that's really what the long bones are providing you, is that nice leverage. Now certainly in your legs, you're resisting gravity, supporting weight a lot there. Now as we saw in a previous slide, the outer portion, the cortical portion of the bone, that's going to be compact. Very dense, very hard. But the intermedullary portion, that's going to be our spongy bone. And notice what we often call the marrow cavity, your textbook calls the medullary. Because again, that's more toward the middle where we're going to find our marrow, both the red and the yellow marrow. And we'll describe the differences between those as we get a little bit further on today. So the shaft diathesis, that's the cardboard stick. The epiphyses, those are the cotton ends. You know what I'm talking about, right? Q-tip. Think of a Q-tip. The cotton ends are our epiphyses, the knobby portions, and the stick, the cardboard, that's the diathesis. And much like we see with the shaft, the outer portion is going to be compact bone, the inner portion much more densely populated with our spongy bone. But on the surface, we have cartilage. And what kind of cartilage is going to make up that articular surface? Hyaline cartilage. Hyaline cartilage is going to make that surface. Yeah, it's going to reduce friction, but it's mostly that shock-absorbing nature to keep bone separate from bone is present on the surface of the epiphyses. Now, I don't like how this division has sort of happened. Now, I understand we've got the diathesis, the shaft, the epiphysis, the top. Then we have the metaphysis here in the middle that we're going to get to next. But really, the bottom of the epiphysis is where we have our growth plate. But for whatever reason, your textbook decided to put that in the middle region, the metaphysis. Now, whether you say the epiphyseal growth plate is in the epiphysis, which I have always taught, or you say it's in the metaphysis because that's what the textbook says, I'm good with either way, as long as we understand that right in between the epiphysis and the metaphysis, you have this portion of bone that only completely forms bone until you're about in your early to mid-20s. Before that time, it was a line of hyaline cartilage. And this hyaline cartilage provided the foundational material to cause your bones to lengthen. And as the cartilage expands and pushes further and further the epiphyses up the shaft, the bones, the cells that are left behind are gradually replaced with bone. And that's what causes your bones to grow until you get into, again, your early to mid-20s, depending on your genetics. But after that point, you won't grow any taller. That's it. Unless you have bone lengthening surgery. And if you look at this, I tried looking at some slides to put it together toward the end, but I'm queasy. That's why I could never be a nurse. Can't do it. But yeah, we'll talk about it a little bit. They cut it, and then they slowly, every day, these people have to move it further and further apart, like a millimeter. No. See, I'm getting hot just thinking about it. Orthopedic stuff, watching people drill into bones and hammer. I could never do orthopedic surgery. So what we're seeing in this illustration is an adult bone in which our epiphyseal growing cartilage has already been completely replaced with bone. That's why you don't grow anymore, because bone is not going to expand rapidly enough to show any increase in your vertical length of that particular bone. Now, just like we saw in cartilage, we have this outer portion of our bone. And we're going to use the same peri terms. But perichondrium was for cartilage. Periosteum, that's going to be for our bone. And on the inside, which inside IN sounds like endosteum EN, that's going to be the lining on the inside of our long bones. Now, do you remember the two layers we had of our perichondrium? I know it wasn't on the test, so I don't expect you to have studied that yet. But we had two layers to our perichondrium. If you learned those two layers, then you already know the two layers of our periosteum, which are our outer fibrous layer and our inner cellular layer. And both in cartilage and bone, even though the cells are different, they do basically the same stuff. The outer fibrous layer is going to be that part that attaches to other connective tissue elements in the body. Whereas the cellular layer of the periosteum, this is going to be where we have the cells, the progenitor cells, the osteoblasts, and yes, some of the removing cells that are going to lay down bone and potentially remodel the bone. And the inside, the endosteum, for all intents and purposes, it's the same thing as the cellular layer of the periosteum. It's just on the inside. And we have, again, those same cells. Progenitor cells, baby bone cells, and the osteoclasts that can reshape the bone depending on the stresses you put your body under daily. So peri, outside, endo, inside, and osteum is just that term that we use to mean bone. Whether we put it as a prefix, osteocyte, or we put it at the end of the word, the suffix, meaning periosteum. We're still talking about bone. The only thing that I'm aware of that really changes with your bones is after you've had a break. And we're going to talk about that probably on Friday. But after you've had a break, the bone doesn't regrow exactly the same. Your bone's always going to be thicker at the side of the break. So that's the only thing I know that really changes over time.
Let's say you put stress on your tibia every day.
Well, if you put stress on the bone, your bone's going to get thicker to resist the stress. The periosteum is probably not going to be any thicker, but the bone completely reshapes and reforms to resist those stresses. Now, I know y'all looked at a bunch of bumps and grooves and ridges. Did y'all happen to find the little hole in the side of the long bones? Maybe that's one you didn't have to name. But this is a foramen, a hole. And this I've always heard as a vascular foramen, but you can also have it described as a nutrient foramen. Because if you're going to get vessels into the bone, you got to penetrate through the outside of the bone. And so the little holes that you see on the outer shaft of the bone, that's where our vessels and nerves will penetrate through, get into our medullary cavity, and then spread throughout our bony tissue to provide the nourishment to the cells, to remove the waste from the cells, and then to have a sensory supply of information. Because once again, we had nerves. We're not going to have motor nerves going to our bones because they're not going to move on their own. We're going to have our muscles that are attached to them make that move. But for those of you, absolutely, and we've already asked this, when you break a bone, it hurts. It's that sensory information that lets you know, hey, stupid, this wasn't a good thing you did. You better get it fixed. But fortunately, because bone is living, bone can and does repair itself. You just have to get it lined up in the perfect orientation for it to do so and to be back to normal. Now, inside the medullary part of our bones, we have this part we call the marrow. And we have red and yellow marrow. Typically, for kids, we're going to have a lot of red marrow. And this red marrow is going to be filled with our blood cell progenitors. And when we talk about these progenitor cells and stem cells that provide our new red blood cells and white blood cells, we always refer to it as hemopoietic or hematopoietic tissue. Heme. What prefix does that refer to? Blood. Because if you have a blood disorder, what doc do you go to? A hematologist. So hema refers to blood. Poiesis is much like genesis. It means forming. So hematopoiesis, hemopoiesis refers to the formation of blood cells. And that's happening in our long bones, especially in children. You're going to find a lot of that red marrow in the bone marrow, the medullary cavity of the long bones. But in adults, that kind of shuts down and we see more of it happening in the portions of our axial skeleton. Now, what part of your skeleton are your long bones? Is that axial skeleton? Appendicular skeleton. So your shoulder, your pelvic girdle, your vertebral column, your ribs, that's your axial skeleton, where that hematopoietic tissue is going to start happening when you get to be an adult. And then the other thing is you get to be an adult, a lot of your red bone marrow when you were a child, that starts to degenerate. And as it degenerates and you have space, it gets filled with adipose tissue. That's why dogs love chewing on bones. They don't love chewing on bones because it's hard and it feels good on their teeth. They're chewing on the bones to break the bones open to get to the rich fatty tissue that's inside. And when you look at a lot of the carnivores out in nature, you'll see lions and hyenas and a lot of the scavengers. they're not just getting the soft, good meat. They will eat through the bones and they will get this fatty tissue out. That's what they're going for. But the good news is this marrow was able to produce cells in children. So if the need arises, some of this marrow may revert back to that same red marrow state to begin to produce many of your blood type cells. Now, your liver can also begin to do that in certain situations because during embryonic development, your liver provided a lot of, especially your red blood cells during development.